has really turned into is overburdening states in objects and then overmutation of that state. And while objects are very helpful, that in itself, the fact that we keep creating states and mutating it, ends up really making our lives a lot difficult for certain things. With the current state of the world, there are a couple of different things that have fundamentally changed. If you have been in the field for about 25 to 30 years, or not even that, maybe I would say if you've been in the field for about 10 years, even that's a good enough number, you probably notice one fundamental shift in the world. 10 years ago, 15 years ago, companies used to make their employees available to you. So you would go to a bank and you would talk to a clerk or a teller. Or you would go to a railway reservation system and you would talk to the person in the counter. So companies or organizations made their employees available to you. Well, no longer the case. Organizations today are making their applications available to you. This is a very fundamental shift in the way business is run today. And when employees are available to you, the rate at which applications can be accessed by your employees is very limited because employees don't scale. But when you have 3 million people who can go access the system and not through maybe 100,000 employees, it's a very different scale you are talking about. So application demand is very different today. Not only is that, we are talking about big data, high volume data, high frequency data, and we are talking about devices. And everybody carries multiple devices, and that in turn ends up really making this a big of a challenge. So when it comes to that, the needs are quite different today. The question is, can we continue to program the way we once programmed? Well, that's where immutability comes in. We'll expand on that. But what are the words really immutability means? Let's talk about immutability in C# just for a few minutes. So here I am in a C# code, and I'm going to say here something like const int max, for example, equals 100, and I'm going to go ahead and display the value of max. So you can see that if a max is a constant, if I try to change it to
and then we can assign this to maybe a variable sample equals, and then maybe we can try to get the value out of this maybe sample. We can output the value of sample dot value maybe and see what the value is. Now in this case, of course, once again, if I were to say sample dot value equals something else, we get an error. But what's the difference? Well, constant is a compile time constant. So the compiler pretty much has to evaluate this and say, what's the value? Read only, on the other hand, is a runtime constant. You can give a value for it at runtime, so different instances of this sample could have potentially different values, but you can only give it the value once, and once it's bound, you cannot modify it. So those two are generally the way we implement constants in C#, and of course the compiler comes back to protect it. However, though, unfortunately, what's the default? The default, on the other hand, is that it is not a constant. So if I were to come in here and say value equals something else, notice in this case the compiler will no longer complain, and of course I'm able to simply go back and see that the value has been modified. So C# tends to fall as a default towards mutability. Now when you think about safe defaults, that is not what C# is doing. It is falling towards not something that is very safe. This really goes back to the fundamental nature of languages. And this reflects back on the time when the language was created and what was really the primary goals of the language. Mutability was not really the choice. That was something you had to really kind of opt into. On the other hand, if you look at languages like F#, so I'm going to say let for example, max equals 4, or let's say 100 again, and I'm going to go ahead and print here, so print, and in this case print, let's say print fn, the value of max. I could try to print the value, and what happens when I try to print the values like this? So in this case, of course, the value max is 100, but what if I say max equals 200? And I'm going to print again, we'll come back to the printing in a minute, and I'm going to run this code, and you may be surprised that it didn't complain at this point. However, if you try to print the value of max that you have on your hand and say what the value is, well, actually, in this particular case, the value of max is exactly what it was before. So you wonder, what in the world happened here? Well, the equal sign in F# is not an assignment. It is actually a comparison. So what you here is, you asked if the value of max is equivalent to the value of 200, and of course the answer is false, it's not. So it was a comparison operation rather than an assignment. Of course, if you ask if it's equal to 100, sure enough it is. So what does that really mean then? Well, there is no real way to modify this value max once you create it. But the real notation for changing in F# is this kind of arrow where you can try to change the value. And of course, after changing it, I'm going to go ahead and print the value here and say what the value of max is. But notice the compiler uses an error on line number 4. It says, of course, you can't do it because max is immutable. So F# falls towards immutability as the default. So the language fundamentally says it should be really impossible to modify the values by default. However, if I do want to modify the value, what should I really do? Well, in this case, if I really want to modify it, I would mark it as mutable. Now, the word mutable is considered to be the keyword of shame. So if you use it, you have to hang your head low, and you should feel really bad about yourself, right, for the rest of the day at least, because you really declared a mutable variable, which is really against the principle of that particular language. Now you can see, because we declared it mutable, you are able to go modify it. But it's easy to find out what variables are mutable and go back and maybe address them separately. So that shows us how we can create this mutability, but immutability is very near and dear to functional programming. So what does functional programming say? Functional programming says we're going to program assignmentless. Now you say, wait a minute, assignmentless, are you telling that we would not modify a single variable once we create it? Well, at least that's what pure functional languages tell us, that we would not modify variables once you create it. The first question then we would ask is that even practical? I mean, is it even practical to create even a small amount of program where we would not modify a variable once we create it? Well, the answer is, it is practical to a great extent. You know the answer to this already. One approach to doing this is to use recursion, isn't it? Because if you're using recursion, what happens? When you are in function, you could do some work, and whenever you want to do some more work, well, you could take a new value, compute the new value, but rather than assigning it to a variable, you could simply call the same function. And when you call the same function, the parameter would be a different instance of the parameter, and that gets a new value. So one way to remove mutability is to use recursion. But that's a very poor way to remove recursion, in my opinion, because there are a couple of different problems with recursion. One, not all problems can be expressed as recursion, and if you do, it is a very contrived solution. You are just making it a recursion only to avoid mutability, and that doesn't feel really nice. The second problem is, recursion, generally speaking, not recursion, but recursion has a limitation. You cannot keep recursing thousands of levels. It will blow up your stack. And that's not fun either, right? So what can we do about it? Well, one way we can solve that problem is to move the mutability to a lower level. Now, let's look at examples of this, see how we can move mutability to a lower level, and then we'll come back and talk about some of the benefits. So I want to total the values And I want to do this with them without mutability. Let's do this in C# to begin with, and then we will see how we can solve this in F# after that. So let's say we have a collection of values. So let's say a list of integer, and I'm going to say values, or we'll call it numbers, equals, let's say, new list of integer, and let's say these are the values I'm going to start with, right? 1, 2, 3, 4, 5, and 6. And I want to perform the total of these values. So when I'm done, I'm going to print the total. So we could say total equal to 0 to begin with. It prints the value of 0 for the total, great. But what would you do? You would say for int I equal to 0, I less than numbers dot count, and then you would say, is it count or uppercase count? Count. And then finally you would say I plus plus. You could write it like this. Or a little bit more civilized, you could say for each, and then you could say, given a variable which is in the collection numbers, you would say total plus equal to the value e. So you would write a code like this. Anybody has written code like this before? All of us here, right? Absolutely. That's called programming. We do this all the time. Well, but this is an example of where we are totally using mutability. In fact, if somebody says total these values, what do you normally do as yourself? You would create an initial value in your mind, take the value, add it, and you're setting that value in your mind, and then you're continuing. Do you do that? Absolutely. And that goes fine until somebody comes and interrupts you. And you get very angry, right? You're like, what? I was counting. Now you ask me a question, I lost it, right? So that's the state we are maintaining, and we get really angry, and that state is kind of thrown off, right? That happens. Yes, please.
What exactly is the problem with, these three,
What's the problem with mutability? Yes, look, I'll come to. Yeah, where are we not doing? Well, come to it. I promise that after we look at the example, I'll come back to the benefit. So just tuned. So we are essentially modifying the value, and I kind of gave you an example already. Like you lose the state when somebody asks you a question, right? That means you better keep that state in your mind. You're so tied to that state at this particular point. Which means, while you're counting, you cannot do anything else. And what does that mean? You can handle concurrently other things. Well, if you can handle it, the code can handle it easier, right? So it kind of gives you a clue. So the point really is that you are totaling the value, and if somebody says, I want to be able to total these values, however, I want to be able to total these values without really changing the value. You might look at this and say, wow, how could you actually total the values without actually changing? Well, let's try this one more time if you don't mind. How about saying, in this case, numbers dot and call a sum method on it? Well, guess what? It works. So why in the world should I do the top code when the bottom code does the job? Well, you may look at this and say, aha, but wait a minute. What does the bottom code do? Maybe they are doing exactly the same thing. Well, if they're doing exactly the same thing, what's wrong with it then? Why shouldn't I do it? Well, let's think about this for a minute. If you have a mutable variable, let's say you have two functions. One function where you get an input, you flow through, and immediately you produce a result. But you did not change anything at all in that function. There is another function where you get in, but along the way you modify a few variables. So you got two functions on the hand. Which of these two functions is going to be easier for you to understand? One where things change, or one where things actually change? The first one, right? Because when things change, let's think about this for a minute. How many people in this room can juggle? Not a single person. One person, and he's reluctantly raising his hand. And how many items can you juggle at the same time? Did you say one? I can't see you in the dark. Three. So can the hand, what is it, a knife? And what else, a grenade? What are things you normally juggle? Oh, okay. I usually juggle my children and my wife. That's really hard already for me, right? So, you're better than I am, I think you're handling it. So while you're juggling, can you ride a bicycle too? I'll give you a clue, yes or no? No. And it's easy things fall apart. How long can you go? 1 minute, right? So what does that mean? It's not sustainable. And so code becomes more complex. That's exactly what happens. Have you ever done this before? Have you looked at a piece of code, and as you're going through the piece of code, you're looking at this code and you're like, it had it. So what do? You take a piece of paper, draw a little column on it, write the variable names, and you're putting your finger on the code, going through one line at a time, have you ever done this before? That's called the lowest point of programming, right? You're like, dear God, I can't deal with this anymore. And when you go through this, everything works fine until somebody asks you a question, you're like, okay, there you go. I gotta start this over again, right? That becomes very, very difficult for us when variables start mutating. Please.
See, the sum example that you given,
yeah,
that's an extension method, right?
I don't care.
No, but then they're not all the extension methods available for all sorts of things. Do you want to create extension methods too?
No. Let's start by using what's already available. Why go for what is not available? That's a great step, right? Because why are you not using any of these? Because life is not good. I don't have everything I need. Why don't you start using what you have already, right? So the point really, yep.
What we're doing, you're mixing the two things. One is like declarative versus imperative programming.
Yeah.
As well as programming in the side function with outside.
What is imperative after all? Telling what to do instead of saying how to do.
The compiler decides. I as a programmer don't decide whether I have to do for loop or for each loop. Let's compiler handle it because.
Agreed. But imperative also has mutability in it.
Well, I don't know.
You do, right there. Poor line number 16.
Now here it is.
Yeah.
There's an extension.
Right.
Which is the
I don't care, because that's the hidden class. We don't care. Well, I'll get to it. Stay tuned. So what's happening in this case? That, right, it's hard to understand, hard to reason, and then somebody comes to you and says, here is a huge collection of values, and you're doing some work with it, and then they tell you, make the code concurrent. How do you make a code concurrent when it has a mutable variable that you are constantly modifying? Is it easy or hard? Very difficult. Because changing a code which is doing mutation to make it concurrent is extremely hard. But thankfully, when we use third-party libraries, what happens? So here's the question to ask. If you mutate a variable, all the problems we talked about is whose problem? Yours. If they mutate a variable, all the problems we talked about is whose problem? Their problem. And one thing you do in life is you always make things other people's problem, right? Then you don't have to worry about it, right? And if you don't like saying it that way, say this is encapsulated. That sounds really nice, right? Which means I don't care, right? So the beauty is, if you do all this work, then it becomes your problem. If they do all that work, it becomes their problem. And guess what? It is their full-time job to write that method. It is not our full-time job to write that loop. That loop is part of what we do. But they get paid only to focus on the library and the APIs. So they can do a lot better job to provide the infrastructure than we have to write the code. So that is called ceding control, and that removes the burden. So that can be your question, right? By delegating this to a lower level, those don't become our problem. Readability, understandability, maintainability, and concurrency. We don't have to worry about all of that. Because the minute we bring immutability into our code, that becomes our problem. So, but we start using these better methods that do the work for us, then it becomes their problem. We don't have to worry about it. So that becomes very, very easy to work with. And so what are the benefits? The benefit, first of all, to begin with is, it's easier to read, easier to understand, but then there is a few more benefits that come out of it. If you have a piece of code, and if the code is not mutating any variables, that function becomes what's called a pure function. A pure function is a function that does not have side effects. When a function doesn't have side effects, so what does it mean, side effects? When you call the function, while the function is running, it doesn't quietly sneak around and modify some variables. This is like a little kid, right? A 2-year-old kid, what does the kid do? Pull pranks on you, right? You are playing with the kid and you suddenly see that, how did you pour all that over there? Well, I was not even watching when you were doing it, right? That's what little kids do. And code behaves like a kid, right? So it makes a side effect all of a sudden. But when a code has a side effect, what happens? It goes and modifies the global state. Well, you call it, and you're looking at this result, and you look around, it's like, well, the world around me has been modified by this code, right? And it becomes really hard to test it. Well, also to reason with it. So a pure function does not modify the world around it, and it doesn't depend on any state that is changing while the function is running. So by favoring immutability, it becomes much more easier to test the code. Imperative code requires a lot more tests than code that does not modify variables. Code that honors immutability requires fewer tests. And you want more tests here. I don't think anyone wants to, right? You want to write as many tests as needed, but you don't want to spend your time writing tests. In fact, a good design will require fewer tests. A poor design will demand a great more number of tests from you. And so it's something you want to favor towards that as well. So for example, I want to double, let's go back to this example for a minute. We went through and called a sum, but what if we want to double the values in a collection? Well, here is the collection of values. Well, what if I want to double these values? Well, in this particular case, in F sharp, we can do a very similar call to list.sum as well and do it, but let's get back to F sharp and say I want to double the values. Well, what do you normally do to double the values? You first again start with a doubled equals new list of integer. So you start with an empty list. You would once again go through for each, and then you would say variable e coming from the value numbers, and you would say doubled dot add, and then e times 2. Once again, you can see the mutability that's in place here. And then once you finish it, you could say double dot for each, and then of course in this case you could print each of the values. So given an element, I want to just print the element that I have on my hand, and you can see that in this particular case the values have been doubled. Alternately, what we could do is, notice that's immutability. That is mutability, but we are doing that mutability. If I come to you and say, this is a very large collection, and I want you to do this in parallel, the short answer is, get out of here, I can't do it, right? Or I need another 15, 20 minutes of writing it, and then a few days of debugging it. And that's a lot of work we have to do. But on the other hand, if I were to do more of a declarative style, like you mentioned, or functional style, depending on how you want to look at it, but essentially the idea behind that is we want to favor immutability in this case. So how would that feel like? So you would say, start with, first of all, in this case you could say numbers dot, and then you can say, well, I have the values, and I want to double them, so I'm going to do a select. So given a value times 2, and then I want to take each of the values, let's put it in a list at this point, and once I get a list out of it, let's go ahead and say dot for each, just like what we did a minute ago. I want to go ahead and print the value. So here's the value that I want to go ahead and print. So in this case, of course, the result is exactly the same, but for one thing, once we get used to the syntax, the code is definitely easier to read. It begins to flow much more naturally. Have you ever noticed this? When you write a for loop, you go to a for and your eyes kind of spin, right? You're trying to go through and say, what's the loop context? And then what happens? The for loop comes and says, it's usually an if statement inside of it. Then it grows a little bit into if with a break and a continue. And what does your eyes do? It goes wild up and down trying to figure out when do you enter the for, when do you exit it, and your head spins with your eyes after that. But when you look at this code, mostly this code becomes a single pass code. You start at the top, you end at the bottom, you went through it once, you're like, yep, that's what. So it becomes a lot more easier to pass through the code to understand what it is doing once you get comfortable with what these methods are. So you're relying on these methods. The question now, we don't need extension methods because these methods are fairly extensible. All you need is to come up with these little methods that you can pass to like select and where, and you can achieve most of your work with it. So rather than spending our time creating extension methods, we can use the methods that are already extensible quite often. So there's so much tool available on our hand that we actually don't use quite often in today. But the beauty of this, as you can see, is that it already gives us the ability to go through this. And of course, which of these two would be easier to parallelize, the top one or the bottom one? Well, the top one definitely is something we have to struggle because of the mutability we're introducing. The bottom one we can rely on other functions that could be easily done because they take care of it under the hood. So immutability opens the door for quite a number of things. First, it is easy to reason the code. You can read the code and you can understand. I had a programmer come to me one day and he said, hey Venkat, I wrote this code and I'm reading through this code that I wrote and I can't understand why it is giving me a wrong result. So this is a big I don't understand why the code is producing the wrong result, right? And I'm sitting and looking at the code and I say, well, if you send this input, it should give you this output. He says, yeah, no, but it doesn't. So we both are sitting here and reading the code like idiots. And then about 10 minutes later, I'm literally putting my finger going through one line at a time. And when I come to like the 8th line, I'm like, hey, did you really mean to take the input and modify it? And the minute I say that, he gets up and he says, you know what, I'm stupid, and he walks away. Because he didn't even realize he's actually modifying an input value given to the function. Now, we all know that changing an input given to a function is poor programming practice. Well, the language doesn't stop us from doing it. Well, C# will not stop you. Other languages like F# do, but not sharp in that regard, right? And why is that such a bad idea? Well, because it's very difficult for us to reason with the code. Our mind doesn't, believe it. It skips over those details. And it's very easy to understand a piece of code that has immutability in it. It is easy to explain to somebody. You don't have all this juggling to show. It's very natural flow. It's easy to test, like I mentioned. But there is another big benefit when we are looking at a piece of code that is not mutating things. So before we do that, let's go to this collection of values that we talked about. So I'm going to say let numbers, we'll call it numbers again, equals, let's say 1, 2, 3, 4, 5, and 6. Well, I want to simply double these values. What can I do for that? Well, numbers dot, and this is going to be a list dot, we can perform a map operation. Well, a lot of languages call it map. This is a bit unfortunate. C# did not introduce lambdas, they introduced link first. And so the words that we use kind of smell towards that. But F# did not introduce link first, right? Yep?
I think C#, if you look at the link is using some of the components, like your closure or anonymous functions, what you are saying, extension methods. So link is built up all these things. So lambda expression was introduced so that you can write anonymous functions inside your query. So C# introduced lambda expression before link.
Not separately though. That's the point. It was influenced heavily by link. That's why it smells like that.
That is influenced by the Haskell actually. A lot of things are.
Well, that's a debatable. We can argue about it separately. I disagree completely. So, but on the other hand, F# really took a step to say, let's really focus on. In fact, F# really is closer to what Haskell does than C# itself. So, in this case, of course, you say list.map. And you're saying, I want to really perform a mapping operation. What do you want to do here? Well, I want to perform a map, let's say a function, anonymous function, and then it doubles the value, and then you got the numbers on your hand. So you're saying, I want to double these values. But one thing I really like about F# is the beautiful composition aspect of it. So you can say, I want to iterate through the values here, and you can say what you want to do per iteration. I could say, given a function, I want to maybe print the values here. So maybe print fm, and then I want to print whatever the value that I'm getting in this particular case. Well, I'm just going to print the value out. So you can double the values and print the values pretty effectively in this particular case, and that's basically what the values are going to go through, a mapping of the values for you to print through. So let's see what the syntactical error here says. So that's coming from 432 is not happy with this. So function E, and I'm asking him to print the value of this particular function here. So I'm not sure why he's not happy with the print function. Well, so essentially the idea behind this is, I'm running into a syntactical error here. So the idea behind this is to really go through the loop and print the value out. So that's basically what map is doing right here to really transform the values. And once you transform the values, of course, you can take the values and you can perform the iteration and print it. So the idea behind this is to really go through the transformation aspect. However, there is one huge benefit that you get out of these kinds of behavior where you don't mutate stuff. So we talked about pure functions earlier. So let's say for a minute, we have a function on our hand, let's say 3 and plus 2. Well, a function or an expression, you can call it either way, which is going to perform this operation. Well, let's say for a minute we have a 3 plus 2, so I'm going to use you as a help. What's 3 plus 2?
5.
Well, he was pretty quick, he said 5. Let's try again, see if he's alert. What is 3 plus 2?
5.
So that's all right. How many times I keep asking him, he's going to give exactly the same response of 3 plus 2 is 5 all the time. But let's change the question a little bit. If I ask him, how much time is left for this talk to be over? First answer is going to be, it feels too long, right? But then he's going to say, oh, it's about 27 minutes more. But what if I wait for 5 more minutes and ask him the question, what's going to be his answer? It's going to be different. Even though my question is exactly the same, the answer is different. Why is that? Because he's depending on something external which is constantly changing, which is the time. Which is even worse. Because one time when you test him, you could say, I'm going to get clever at it. I'm going to call him and measure the time and see if he gave up the right time. And when you call him, you measure the time, well, when he got interrupted. And he took a little break and can come back to do it, well, that's now no longer the same time because the time is constantly varying outside and is depending on something that's changing. Well, that becomes really hard to test. But there is yet another benefit that we get out of this as well. So if you're alert, I've got another question for you. What is 33 plus 75? 110. Did I hear 110? 108 for those who can do math, 10 for can't. Okay? You said 108. Let me ask you this question. What is 33 plus 75? 108? What is 33 plus 75? Come on, I want answer. Louder. Did you notice the difference? What's the difference? Every time I ask, did you see any difference at all? It's faster. Why is it faster? Because you know the answer already. How? It's cached. How could you cache it? What made you cache it?
It's not getting changed.
Because what?
It's not getting changed.
It's not going to change. It's not going to change any number of times. You knew this, right? But if the plus was not a pure function, would you dare to cache it? Right? You would compute this every single time, isn't it? So as a result, when a function is pure, you can optimize it a lot more. You can start optimizing it. When a function is not pure, you have to recompute it every single time because you can't predict what the result is going to be. And that makes a big difference in terms of our ability to optimize, well, mostly compilers' ability to optimize. So compilers can apply memorization techniques. Not only that, we can employ memorization techniques as well in our own code. A slew of problems called dynamic programming heavily relies upon these kinds of techniques where they introduce heavy amount of recursion, where there's overlapping recursions, but then they say, hey, we computed this once, the next time you call it, I can simply return back the result I've already stored, and so they can improve the performance. The computation can come from an exponential time down to potentially a linear time. And that can be huge benefit in terms of algorithms we can implement. Well, if I tell you that my functions are not pure, and they're going to have mutability all over, then you're going to say, I can't do anything with this, right? I just have to call this every single time. It makes even no sense to even come close to applying memorization in that regard. This also leads to other benefits like referential transparency. Well, referential transparency is where you can replace a computation with the value of the computation as long as the result will be exactly the same. which means it gives you the ability to reorder computations. Reordering computations give you the ability to perform a huge amount of optimization. Compilers do this constantly. And compilers would not be able to produce better optimized code if they cannot make assumptions on your code. Languages like F# can make better optimization because of the purity. Because at the very language level, you are defaulting to the purities. Whereas in languages like C# and Java, you're defaulting to impurities. Which means the compiler says, well, I better be careful in this code because I don't want to make sure, I don't want to mess up the correctness of the result in the process of optimizing. And we do get into problems from time to time when the optimization thinks one way and the code was intended for another way. We get into troubles at that time. So those are some of the key benefits. So to go back to your question, those are so many reasons why. Every single one of them may not look like a great big deal, but once you start collecting them all together, that becomes enormous benefit in the long run. And once you kind of get into the habit of writing code with that kind of mode, you feel like a lot of burden has been removed from your shoulder. The code becomes a lot more easier to write, expressive, easier to understand, and it's easier to modify as well.
I have a question.
Yeah.
So can you actually give, like, because I am having some difficulty understanding the concept, can you give a very simple example where you say compiler finds it easy if it's a pure function versus if it's a impure function?
Yep.
So can you give like a very small example to help better explain?
So I'll give you a very trivial example.
Right.
I've got a variable which is a constant. I've got two threads running.
Right.
Both the threads read that variable.
Right.
The compiler says, it's a constant. There will never be a race condition on it. It can either cache the values on each thread, or even let them, actually potentially does because it can bring it to the cache. But the minute that variable is a mutable variable, the compiler says, oh, is there a synchronization primitive now? When do I bring the data from the main memory to the working memory? When do I put it back? A lot of concurrency problems purely come out of shared mutability. That's one example, right? Another example is when you have one example of this which I ran into, this was a while ago, but we had an application where we were using a C++ compiler. We did not modify the code at all. This is exactly the same code, right? So we're sending it through compiler 1, and we're running the application where we know what the result is. We got an output file sitting there with the sample input and sample output, right? We took exactly the same code, no change at all, but we're running it through a newer version of the compiler. That's all we were doing, no code change. Well, the result is not the same. And we're sitting there and scratching our head, why would the result not be the same? What is different? Well, it took us an enormous amount of debugging. Eventually, we found out was a function which was like a plus b plus a plus 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 and something like that, right? So right in the middle, you have a mutation right there, right? So it turned out the two compilers for the same language, one said, I'm going to order these one way, and the other compiler, just an upgraded version, said, I'm going to order them differently. The ANSI standard says, I will not tell you how to do it. So the compiler writers have the right to change it. So if you start mutating things in expressions, really bad things like that can happen. And the net result usually is a bug. And we spend, if you're lucky, hours, but usually months. And once you find it, you hang your head low and say, damn, we shouldn't have done that. And then you have a coding standard in the company that passes around, right? That's where these things come from. Whereas if your function is pure, well, there's no ambiguity there for the compiler to deal with, right? We see this quite a bit happening at the G level, which is even worse, right? So when you're taking your C# code, for example, your C# compiler may produce an IL, but that goes through other layers of transformation during runtime. And when they start performing optimization, and when you start seeing different results, very difficult to track them down. And when you do eventually, it comes back to saying, oh my gosh, we shouldn't have done that. So this can become extremely hard to track a lot of times. And it's even worse. You may not even see that it's broken for a long time until faithfully a combination of optimizations come together, and then that's when it flares up, right?
One other thing, so you talk about immutability and you gave some examples like sum and whatever, right? So these are simple examples. In a more complex application, like, first, the problem I find with lambda expressions is it gets ugly too fast.
Definitely not true. You made it ugly to pass.
Right.
Let me emphasize that. A lambda, so it's extremely important. As professionals, we have to be very vigilant of what we do. Right? We cannot blame the world around us for our stupidity. I see programmers do this all the time. A lambda is a glue code. A lambda is literally a glue code, which means what you do is you come into a lambda and you say, well, this is exactly what I want to do. You say, wait a minute, no, I don't want to do something simple. I don't want to print it. I want to apply a fast Fourier transformation. So here's the wrong thing to do. That's stupidity. There's no reason in the world to do this. What you do is you say, okay, no worries. That's what I should do. Right? So it's not ugly. It's, and the better news is, how do you test a lambda which is long? You can't. Whereas now you can test the fact. So these are senses we have to develop, right? So when you start writing code, you say, no, this is a lambda, it's a glue code. All I have to do is step here and step to this other function, and I'm done. So one rule I follow is, don't put curly braces and put a boatload of code in there, right? But this is where you need to work with your colleagues and say, hey, we don't do this here, right? And then you're not having the problem. So we can't blame the lambdas for that. We got to blame ourselves for that. So then it becomes easy. Then you need to ask yourselves, what is the real purpose of this code? This purpose of this code is to say, I'm putting the data here, and I'm saying do that operation. It's a declarative code. Well, once you put a lot of lines of code, it's no longer declarative. We get into this temptation a lot of times. Like, people write JavaScript, like there's no tomorrow, right? Bulk of code, and then a curly bracket, comma, function again. It's like, dude, what's this? Right? It's completely unreadable. But not because JavaScript is unreadable, because we worked hard to make it unreadable. Same thing in every language, right? Every language, my good friend, the language says, programmers will move heaven and earth to write bad code. It doesn't matter. Give them the language possible. This guy will show you, here's how you write ugly code in it. We have to work really hard for that, right? So lambdas doesn't have to cost that at all. So what we need to do is, simply this becomes a glue code. In fact, this is so beautiful, you could completely replace this with something even more simpler. And it becomes even more elegant to communicate after a while, and we have to work towards it. Writing code requires a little bit more vigilance on our part. But once we do that, then whenever people say that some code is complex, yes, it is complex because we made it so. It doesn't have to be, right? So you can, Einstein said, any intelligent fool can make it violent and complex, but it takes a touch of genius to make it simple. We can make things simple, but the problem is when you make it simple, people look at this and say, gosh, I understand it. I don't have to think. And you feel really let down, right? You say, well, I want you to hurt. I want you to have stomach pain looking at my code, right? And then they come back and say, you're really good. I couldn't understand your code. We have this negative culture in our field, right? We got this negative culture. We got to turn that clock back and say, no, I take pride in writing simple code. I take pride in things people actually can use and benefit, not create a monster out of it. Have you ever seen somebody sitting next to you and say, you ask them, what are you working on? And he says, you know what, application, it works, I go home on time, and we make money. Have you ever heard anybody say that? The guy says, I work on a code which is 3 million lines of code. Boy, we work every night and day, and it sucks. And then you say, what does it do? Oh, it's causing ulcer. Not to you, but for the company, right? We don't know that yet. That's a negative culture again. We've been working towards that. We got to fix that. So given this, where does this lead us? It leads us towards ability to access laziness. Laziness is a very interesting idea. But laziness is not even possible if you have impurity. Why is that? Laziness says, I will not do it now, I will do it later. Here's an example of laziness. My wife sits there and says, hey, you have to do your work. Yes. Now you have to do this too. Yes. Well, while I'm doing it, you got to put the trash out. Okay. Do it now, I'm calling daddy. Okay, I do it now. That's laziness, right? That command that if you don't do it, I'm going to call daddy is when it triggers this execution. Well, but this is only possible if you don't have a side effect. Why so? Because laziness says, if I don't need to do something, I won't even do it. Now think for a minute. In C# you're calling a constructor. Once you call a constructor, you say new my class parameter semicolon, and what does C# do? Goes on, creates this object only to throw it away. Like why do that? If I never use this object, I've never even assigned it to anything, why in the world are you creating it? Well, C# says, because you may do a side effect in the constructor. Right? That's the language's thought, right? Because you could do a side effect in the constructor. And if I never call the constructor, you're going to come back crying with, about it, right? But if a language gives you immutability, what does that mean? Well, I'm not going to cause any side effects over there. I do some work, and I give you a result, but if you never use the result, then nobody cares whether I ran it or not. And that is a huge difference, and that means I can be lazy. You can never be lazy if you don't have purity. And this is why languages like Haskell push it all the way to the extent. In Haskell, you got to declare a method as impure if you ever cause impurity. You put IO on it, impure operation. If you never declare it impure, then it says, oh, this could be pure, I can make it lazy. But the minute you say it's impure, it can't make it lazy. It will not optimize it. So laziness is very affordable when you have immutability, which is very difficult to do otherwise. And so as a result, we can employ laziness. Let's look at one example of this, how convincing the code really becomes. Let's look at this example for a minute and see how expressive this is. So I'm going to say, here's a list 1, 2, let's say 3. Now I'm going to say 5, 4. Notice the ordering here. 5, 4, 6, 7, 8, 9, and 10. So now here, I want to say, given the sequence, right? I don't care about any other sequence. Given the sequence, find the first number greater than 3 and even. So find the double, let's say double of the first number greater than 3 and even. So what do we normally do? Int result equal to 0. And then we say print the result. Then for var element, so for each rather. So for each var element in numbers, and what do? If element is greater than 3 and element mod 2 is equal to 0, then we say, well, now that we have the value candidate, result is equal to e times 2, and then we break. So this is a code we all have written at some point or the other, right? But the problem is, this code is broken. You know how it's broken. Until the customer comes to you and says, hey, your code sucks. And usually I say, don't tell me the obvious. I know my code sucks. Tell me how it sucks today. That's what I don't know, right? So the customer says, I tried this code with an empty list. The result is 0, not 0. It's non-existent, right? Or I tried this with the value where there's no even number. I tried it with value, there is no value that's greater than 3. We don't even handle any of those. But let's try this one more time. What about if we say, for example, output, and what am I going to say here? Well, I'm going to take numbers, and I'm going to say where, given an element is greater than 3, and I'm going to say where, one more time, given an element mod 2 is equal to 0, and then I'm going to say, well, select, and what am I selecting in this point? I'm going to say given an element, give me an element times 2, but only give me the first one. So I can run this code and I can get the same exact result. However, you look at this code and say, hey, wait a minute. What if I had 1,000,000 elements? Are you crazy? Because you're taking 1,000,000 elements, find every single value is greater than 3, and among the result you are trying to find out if everything left is even, and then you are doubling the whole world that's given to you only to give you the first one, right? That's stupid. Well, but the beauty is, they knew something here, or they are betting on something here. What are they betting on? What is it? Immutability. They're betting on that line 25, 26, 27, those functions are pure. And if those functions are pure, what does that mean? Nobody cares if you never ran them. And they say, oh, here's what we could do. We will only run enough of them to produce the result. So literally what they do here is they never run any of these calls just to show. I kept telling don't do any purity, but just for us to be able to peek into it, so entertain this thought. So I'm going to change this to, let's call it as is GT3 for a minute. So I'm going to write a method public static boolean is greater than 3. Let's write it as is greater than 3. And what am I going to do here? Well, given a number, I want to simply say return number greater than 3. That's all I'm going to do, right? I didn't make much change to this code other than just writing that. Now that I have written that, just to entertain this thought, and this is why you shouldn't do impure operations in these functions, I'm going to say e is greater than 3, so e is greater than 3 called for, and let's just take a look at what we're sending here, number. Now notice my sequence was 1, 2, 3, 5, 4, and then a slew of 6, 7. There could be a million values after that. I don't care how many values are there. But when I go back and run this code, notice what it did. It only evaluated enough. It never ever touched values 6, 7, 8, and 9. Why? Well, that's laziness. It says, I don't need to work so hard. I don't need to do all this extra work. All I have to do is simply do enough work to get you the result. Well, that's kind of an optimization baked into this, isn't it? So this says, because these functions don't have any side effect, but if you had side effect, what will happen? You run the code without laziness, and then you run the code with the laziness, and you say, wait, this is not going to help. The output is not the same anymore, right? So that's why the purity is extremely important in these cases. And in language like Haskell, they consider input and output as impure, and they are, right? We can't just go around and do input-output all over, please.
So can you explain again, how it,
How does it do this? So it says, I am not going to take the entire collection and run this first. It doesn't do that. And then produce a sub-collection and then run this. Then run this. It doesn't do that. Instead, what it does is it says, you know what? Let me explain to you a little differently. You probably know this already. You know, when you go to work, you know some people at work like this, right? You go to work, you're sitting and busy working. There's one guy comes to work in the morning. He sits down, stretches his hands, looks around and says, hey, where's the boss? You say, well, the boss is out sick today. And the person says, yes, I don't have to do any work today. Right? It's kind of like code. So notice in this case, when I run this code, just to entertain this thought, I'm going to come down here, and I'm going to say output, let's say done for a minute, right? So I'm going to change one more thing. I'm going to remove that function for a minute, and I'm going to end with the first. Just entertain this thought for a minute again. You can see all of that. But now, I'm going to comment out only the first, and run this code. Notice it never ran the other code. And the reason is, these are a bunch of lazy guys. You call this and say, hey, do the where. Done. It's lying to you. Hey, do the where again. Done. Do the select again. Done. Now, find the first one. It's like, oh my God, I got to do some work now. But if you never call first, it's like, this is cool. Right? Remember when you were in school, you were the guy who was working really hard all the time, studying all the time, and you had this other guy who always played around, never really cared about anything, and you always looked at this as what a loser, right? And then the exam day comes and you're like, this is awesome, I'm going to show him the world. And it pours rain everywhere, and the school is closed. And the guy is sitting there is like, I told you. It's kind of like that kind of code, right? So the first says, hey, give me the result. And the other guy's like, hey, force is not at work today. Why do the work? So in other words, the optimization is, this is all baked under the hood. How do they do this? They said, we don't need to linearly run through the collection. Let's take one value, drop it down, see if it hits the bottom. If it does, we're done. If it doesn't, start with the next one, and the next one, and the next one. So if they take all these calls, because they are lambdas, they can connect them using functions. And then they evaluate them in one chunk only on demand. The demand comes from these terminal functions, like first. So enormous amount of optimization goes in, but they couldn't possibly do all this optimization if we didn't promise purity. C#, of course, says, you don't want to promise purity. If you don't promise purity, it's your problem, right? Well, other languages take a different take and say, no, you'll enforce it using compilers, you better promise purity for us, right? It's a difference in the style of languages. Same thing with Java, right? Just like C#. We got to be careful. It's our responsibility to guarantee purity at these points. But you cannot even imagine having these kinds of capabilities in the languages. Now, this is something to think about, right? This is an enormously powerful feature that's in the language. How sad if we don't make use of it?
Only because it's an integer and I have written.
Anything. You can say, here's a collection of in this room. Everyone in this room. I want to find the first person with a blue shirt. And who is older than 25 years old. And who has a mustache.
But without actually executing it, how can you eliminate the other?
It executes enough. Right? It executes enough. That's where the smartness is. It says, so I'll explain this to you. When you're being chased by a bear, it's not how fast you run. You just only have to run faster than the guys behind you. The code is saying, I don't need to run really fast. I need to run smartly. So it says, I need to run only enough to produce a result. The minute I produce a result, well, let me put it this way. We already know this answer, right? When you do an if statement, and you say condition 1, ampersand condition 2, ampersand condition 3, what does the compiler do? That's obvious to us. Well, how could the compiler do an if statement without running through all of them? Well, that's called short-circuiting. Well, that's short-circuiting in a different way, right? So compilers can say, I don't need to run all of this. And the way they do that is by putting those functions together and saying, take one value, run it through a chain. If it didn't reach the end, then run the, it's an iteration. But it's not an iteration horizontally, it's an iteration vertically. It says run through one value. If you want to come to the end, then try the next one, not otherwise, right? The first is the trigger here. And if you never know the first, you never said stop loop. So it's a first that causes the value to start going through the chain, through the pipe. So that is basically what's happening in this case. So immutability also makes parallelization affordable. Now you can start parallelizing code much more effectively. How could you start parallelizing? Well, if you have a range of values, you can then say, well, given this range, I can use a couple of different things. You can say, for example, you can say something along the lines of, let's look at one example here. You can say, well, I have an enumerator. So you can say enumerator, enumeration.range, and you can start with, let's say, 1 to 100,000. Or you can say, well, I don't want to start with that, I want to start with a parallel enumeration. But the rest of the chain wouldn't care whether you start with an enumeration or a parallel enumeration. And you can have it control it. So as a result, what would happen? Well, you can start parallelizing the code much more effectively. But I want to answer the last question. But does parallelization, does programming with immutability really mean we have total immutability? Well, the answer is simply no. Because if nothing ever changes, then there would be any meaning for a program to run. Because ultimately a program has to cause side effects. Right? It's got to produce an output. If you look at your file system, you cannot say, here's my hard drive, I'm going to run this program, result is another hard drive. Right? It's got fundamentally at some point it's got to change. Right? And what is that point where it actually is going to change? What is that level? So I want you to think about this a little differently. If I tell you I want to program with immutability, I can't go forever with this. So what I'm going to say is, I'm going to create what I would like to call as a circle of purity. My circle of purity is everything in the circle is pure. And I'm going to keep increasing that circle as much as practical. And a way to think about it is this. I don't think we have this here in India, at least not in the places I know. But in several parts of the US, and it's not common in every part of the US also, in several parts of the US, we got what is called zoning. Zoning simply means you cannot have a liquor store and a school next to each other. Very simple, right? You have a liquor store and a school next to each other. So there'll be a big road. This is all residential and this is all commercial. And things that you want children's playground over there, right? So they have nice separation. Here's where children are, here's where commercial happen. And so you can think of as a zoning for your application where you have a circle of purity, and within the circle of purity there will be no mutability. And then you have a very thin ring of immutability around it, impurity around it. This ring of impurity is where you would read from files, write to files, read from database, do all the impure operations. Then what you do is you keep your impurities in the peripheral and make your circle as big as you can. And then within that circle, of course, you can be very efficient for laziness, parallelization, and stuff like that. So it requires a bit of a rethinking of the way we design software, and then we get to benefit from that. So as much as possible, start providing immutability, and when you can't, push that to the boundaries and say, until I figure out. Another thing to think about is this philosophy of make it work, make it better. You don't have to solve all the problems in one setting. It's impossible to create code in one setting like that. So create a code, come back and refactor it and make it better. And that's a much better way. But the beauty is that we have the tools on our hands already. These are already available to us in the languages we use. What we need is our will to actually start programming this way and change our line of thinking. Then it becomes extremely powerful to be able to use that. I hope you found that useful. Thank you.